Okay, so I'd like to challenge your view of maybe what we believed is reality so far, and maybe maybe that it's just an illusion, and that reality is somewhat very different than what we think it is. So this is a picture of 3D hyperbolic anti-de Sitter space, and it has negative curvature. Now, why would it look like this? It would make sense if we were thinking about these little quantum states over here, thinking about one quantum state pointing in this direction and the other one pointing in this direction. Then we could have two entangled quantum states and they would have some negative curvature between them. Okay, and we would have state A and state B over here. Um, well, this is going to be a 3D space. So what's interesting is that um, well, any hyperbolic distances are actually require complex numbers, which is kind of interesting. So it implies that this is a 3D complex space, and that's fine because we need a 3D complex space to represent wave functions. So we're able to represent wave functions in this space, I suppose. But the idea here is that we have this negative curvature, and if we have quantum information inside of this space, we can extract it by taking a little slice. And when we take the slice, we see this little boundary appearing. Of course, the boundary has positive curvature. And so essentially we have this two-dimensional slice here, which is kind of this holographic projection of this negative curvature quantum space where wave functions sort of exist. Um, and and so it appears that on our retina, on our lens here, we have this area that essentially appears, which is this area right here. So this area appears as the wave function source comes from this negative curvature space and sort of appears as this area with positive curvature in our lens. Now we have two eyes, okay, so that's what sort of helps us get depth perception. But the problem is that there is no depth, it's just intensity. Okay, so like you're getting different intensity of, of light from each of these sources, but this is just a two-dimensional slice. Right, and that's absolutely true because again, you can't see both sides of an object. You can't see in 3D. You can really just see in 2D. You can see a slice of life in front of you, and you can see different intensities of light, which sort of give you this illusion that there's depth. That's just an illusion. So you can turn around and sort of view this stuff from all sides, this 3D hyperbolic space here. Well, this hyperbolic space is complex, and what we see as real is just this two-dimensional area, which is sort of this mental model, or really a construct that we make in our mind when from viewing this space from all three sides. And so you can develop this spherical illusion if you just kind of rotate this around. And so we can see that our 3D space is simply just an illusion. What we're seeing reality is actually just this hyperbolic negative curvature space, and reality is just this little illusion that we make uh, because we have this sensor the sensor on our eye, this retina that can encode this quantum information and sort of project it as an area through intensities onto this lens that we have. So it's just kind of interesting. And here is another way that we can uh, this 3D illusion can be represented as a mathematical model. So you can see that we have length, width, and height, and we call it a volume. Length, width, and height in meters to the third power, right? That's just a 3D model. It's a mathematical construction that we have. And this is a 2D screen. You can see it's just 2D. There's really, even if you look at me, pull out a, even if you look around you, like again, get rid of the whole idea that there's a third dimension and just just relax your eye a little bit and you'll notice that it's really just two dimensions. Okay, and the illusion will disappear. So I can sort of switch between this sort of 3D sort of perception. You can sort of try to look past an object maybe and sort of pretend like there's a third dimension. But really, just think about all the borders, okay? And now the borders simply just fade into each other, and now everything just becomes this uh 2D level of intensities. And then everything, because you essentially, even if something was solid, like my hand here, but what if it was made of smoke, my hand, and I could pass my hand through the smoke? Well, what if we took, made the smoke cold enough that it froze, and then all of a sudden now it's not passable anymore? So there's a certain point where these quantum states become impassable, really, if you try to go through them. But uh, but everything is just waves, and so that's why there are things that can still pass through that solid object. It's just a it's just a it's just a quantum measurement that you're making as you're passing through it. It's a quantum measurement that tells you what information is there. But again, it's an illusion, positive curvature illusion of this negative curvature space that we can sense with our quantum sensors, which are going to be, our five senses that we have. Um, and anything. So those are going to be the ways that we can sort of collapse the wave function and make these measurements on an anti-de Sitter space. This is quite interesting. I think that this helps to get a more solid model of quantum gravity.